Howdy, y'all. We're live a little early, or not early. We're live on a bonus day. Um, I still had more physics problems to go over yesterday that I didn't get to, and I want to, and I have the time today. So, bonus stream. Um, let's check our volume. Let's check our volume. Volume's good. Um, okay. I'm still getting some stuff set up. I just wanted to get the I needed to get the stream sort of launched. Um, so excuse me for a moment while I get the rest of my stuff set up and ready to go for the stream. And I'll be back and we'll get started and I'll work through another couple of physics problems. All right, see you in a couple minutes. All right. Testing. Testing. Cool. Volume's good. I'm back. I want to try to be good today about making a note of the timestamp in the VOD when I start answering each question. So along with the question, I want to just like write down the time. It doesn't tell me where. Oh wait, no, it totally does. I do have a stream counter right here. Excellent. Okay. I was like, I don't think I have a thing that tells me like what minute I'm at, what second I'm at in the stream, but I totally do right here. So I want to make note of that, and I want to use the stream marker thing as I'm answering each question so that I can link to each one. Oh, I need my glasses. I mentioned yesterday that my new anxiety meds are working pretty well, which means I can, this is decaf coffee, but I can drink I feel like I can drink coffee again. For a little while there, even decaf coffee was just like spiking my anxiety. It was just awful. But we're feeling a little bit more even keeled. That's really nice. Makes things feel possible, you know, such as doing a bonus stream. All right. Let's get rid of this. Let's get rid of that. Stream is now starting properly. We start the stream by saying abolish ICE. We'll say it till it's done. We'll vote that way. We'll protest. We will show up and we'll oppose a fascist secret police. It's just unbelievable. We don't have to tolerate it. It's not something that belongs in our society. So we will abolish them, and it will happen. All right, but for today, for now, right in this very moment, there are two more physics problems. These ones are kind of longer, so but let's okay. So here's our first question. Oh, all right. So we're at 15:15. How do I want to do this? Timestamp is, we'll call it 1530. Okay. So underlines. Oh wait. There we go. Oops. Excellent. There we go. Timestamp. Okay. Except because I've been sitting here messing with it, it's more like 1645. But that's totally okay. There we go. Also at a stream marker. Boom. Okay, I did it. Good job. Okay. Pulling one of two blocks. Okay. So we'll look. The order of this is weird. It has the questions, then it has the situation. Only one of these is required. The rest are like optional, which means I guess is extra credit. Draw the force diagrams for each block. This is a good one to think about carefully. Okay, so we're doing force diagrams first. Show that this expression right here gives us the acceleration for the two blocks together. And to show that the final numerical answer is 1.7 seconds. So there, I assume there's a question down here. All right. So this is from this is a textbook problem. The coefficient of static friction is 0.6 between the two blocks. The coefficient of kinetic friction between the lower block and the floor is 0.2. Force F causes both blocks to cross a distance of 5 meters starting from rest. What is the least amount of time in which this motion can be completed without the top block sliding on the lower block? The least amount of time because a force on it, a constant force creates a constant acceleration. And if we go too fast, we will overcome the static friction. If we apply too large of a force, we will overcome the static friction between the two blocks, and the top block will slide. Yeah. But we want them to stay exactly how they are. We want to use the friction between the two blocks. To keep them together. Okay, let's. Okay. So first thing we want to do is draw these force diagrams, these free body diagrams. So we're going to do top block here. Oops. Okay. And so we have a normal force coming up because we have a gravity force here, which is mass times gravity. We have the applied force right there. And of course, we then have the force of static friction, and we don't have to worry about the force of kinetic friction between this block and the bottom block because we're not going to pull it fast enough to overcome the static friction. Okay, cool. That should be everything, right? Don't forget about your normal forces, because your normal force impacts your friction force. Okay, so bottom block. Of course we have, let's call this mass T times G, right, for the top block. So this will be mass B for the bottom block times G. There's of course, so this is the normal force on the top block. There's of course a normal force. Actually here, let me do this. This is the block itself. The bottom block has its own mass, so its own weight, but the weight of the top block is also pushing down on it. Right? There's that weight pushing down on it we can't forget about. There is a normal force. It's the normal force on the bottom block. There is a forward force, which is the force of static friction between the two blocks. And then there is an opposing force. This is a force of kinetic friction between the lower block, the bottom block, rather, and the surface on which it rests. Excellent. That should be, this is, yeah, the reason the whole thing moves forward is because this friction force, which is backwards on the top block, opposing this force, equal and opposite reactions, right? That means it has to be pulling forward, or to the right. And let's give ourselves a little frame of reference here. We'll call up positive, we'll call right positive. That's our default, but it's always good to just write it down and define it explicitly. Okay, that's neat. We got that. One thing I'd be excited about once if I ever get viewers here is for people to tell me, like, if I've forgotten something. It does, like, I watched, there's a Minecraft streamer, Tango Tech. He's a hermit. As in he's one of the people that plays on the Hermitcraft server. I watch his streams a lot because he's building a game within Minecraft. And so he's doing all sorts of just weird construction stuff and very technical stuff. And so his chat is always chiming in with kind of helpful things, but like, there's some people in there that like really know what they're talking about, and other people that are just basically taking guesses, and the people that take guesses aren't super helpful. But he ultimately, it seems like having the chat there while he's working on stuff is a net positive for him. It makes things more efficient for him. He doesn't have to go and like, there's more ideas generating. And then he just has to rely on his own intuition about which suggestions seem viable. But okay. Oh, you know what? Ba, ba, ba. I think I'm going to relabel these. Here, I'll show you why. Let me Let me paste in this next question. So notice that it wants to show the acceleration is this, but it's using m1 and m2 for the masses. So let's go ahead and change these tops to ones and these bottoms to twos, which is, I assume, how they're figuring it. But I don't know. Maybe they numbered them in reverse. They didn't actually say in the problem. See, this is the problem with bad homework problems, right? Is there's like all of this sort of implicit stuff where you're, and this is what causes students a lot of problems. They're like, what's M1 and what's M2? You can sort of take a guess, but you don't know, right? You just need. Maybe I should be an editor for textbook questions or something. All right. So the acceleration of the blocks, they have it labeled as A2. And when we get this, if our ones and twos are reversed, right, we have 2 on the top and 1 on the bottom. In these little situations, that just means we numbered them in reverse, and we'll reverse our numbering on our diagrams. It says A2, which I assume means the acceleration of the bottom block, which is really the acceleration of both of them. Okay. So we're going to do, so we're still top block. This is top block horizontal. We don't have to worry about the vertical here much because it's not moving vertically. So we know the sum of the forces on this block has to equal its mass times its acceleration. So mass 1 times the overall acceleration. Okay. And actually, I'm going to start writing this in reverse because we have to expand the sum of forces here. So M1A equals the sum of the horizontal forces, right, in the x direction. So this is going to be M1A is equal to the applied force F plus Fs. But we don't want Fs in our thing. We actually don't want F either. So this is going to be the applied force plus mu of static friction times that normal force. But that normal force is just what's balancing the vertical forces, right? And so we get M1A is equal to the applied force plus the coefficient of static friction times M1G. Neat. Okay, so this is where we're starting off. I don't know how we're going to want to rearrange that just yet. Notice we have M1 on both sides. Could be worthwhile to get the M1s on the same side, but meh. We'll see what we need when we get there. So bottom block. Horizontal. So we have M2A is equal to the sum of the forces in the x direction on this one. So we have M2A is going to equal that force of static friction minus the force of kinetic friction. But we already know that force of static friction, right? We expanded that. We already expanded that right here into mu s m1 g. That force has to be the same, equal and opposite reaction. Okay. Then we want to subtract from that this, which is going to be mu of k kinetic friction times the normal force on 2, but the normal force on 2 has to balance. It's not just its own weight that's being pushed down onto the table, and therefore the table is pushing back. It's the weight of both blocks. So this becomes K, and then all of this is actually the sum of a couple forces, M2G plus M1G, like that. Okay. Now we ask ourselves how we put this together. Oh, okay. Well, I think we actually have it right here. Look at this. Okay, check out what we can do. Both of these accelerations have to be the acceleration, right? So what we can do with this one, because this one is only concerned with sort of these internal bits, right? So like the bottom block is sort of removed from that force. That force isn't being directly applied to it. It's being transmitted by the static friction. And the static friction we can write purely in terms of these other sort of more internal things. So we're gonna solve for A. So we're just going to do divided by M2. That's going to cancel out. So we'll divide it by M2, and we'll do divided by M2. And so what we get here is we get that A is equal to the coefficient of static friction times gravity, then times M1 divided by M2. And then from that, we're going to subtract. I'm going to factor out this gravity and divide in this M2. So we're going to have coefficient of kinetic friction, gravity, and then we're going to have M2 over M2, which is 1, plus M1 over M2. And now watch what we can do. I can rearrange this any way I want. A equals, so what I'm going to do is I'm going to write this as mu s m1g divided by m2. All the same thing, right? Mu, g, and m are all being multiplied, and then it's being divided by m2. So we can do that in whatever order we want there. Minus, same thing here. I'm going to call this, I'm going to put this mu k, and I'm going to have that multiply, and this addition, I'm going to switch the order up. M1 divided by M2 plus 1. And then at the end, I'm going to multiply by the gravity. And look, we have exactly the expression. So we must have labeled our diagrams, our block 1 and block 2 correctly. Good for us. Boom. There we go. Like such. So notice we didn't actually end up using any of this for this part of the problem. What this tells me, okay, well, there's that. So let's move on to the next piece, shall we? Okay, so show that the final numerical answer is 1.7 seconds. Numerical answer to what, though? The question was, what is the least amount of time in which this motion can be completed without the top box sliding? on the lower block. So that's what we're talking about in terms of time. What is the least amount of time? So we want to figure out what this acceleration is. And I think we can do that by just so actually, how do I want to do this? So it starts from rest and it goes a distance. So we want to use the kinematic equation. Delta S. Well, actually, you'll have seen this, or I often write it as final displacement equals initial displacement plus initial velocity times time plus 1/2 acceleration times time squared, right? But if we subtract over the SI, final displacement minus initial displacement, that's just change in displacement. So we can write it like that. T plus 1/2 AT squared. But we know initial velocity is 0, right? So this becomes delta S equals just 1/2 AT squared. So if we solve for T, so we'll divide by A, but multiply by 2, right? That'll cancel out, that'll cancel. Actually, let me do those with 2 different colors. Divide by A, so we divide by A. Multiply by 2, so we multiply by 2. And so we get 2 times delta S over A is equal to T squared. And so, of course, we take a square root. And that leaves us with T. The amount of time it takes to make this acceleration is the square root of 2 delta S over A. Boom. Okay. And then we know what our A is, right? And then we know delta S equals 5 meters. This is given. We know that A is equal to mu S. Oh, I have it written right here. I can just, okay. Mu S M1 G divided by M2 minus mu K M1 divided by M2 plus 1 also times G. There we go. And this is from part B. So we want to like set this up. We want to plug this into our calculator, our TI, right? And so what we need to do is let's rewrite our variables and say what their values are and what we're going to call them. We'll rewrite our formula, our formulas, with the new notations, right? So okay, so we're going to call so we're going to call, let's start up here. We're going to call delta S. We're going to call that we're going to use D for distance. That's delta S. That's 5.0. Okay. We have to calculate acceleration. So we'll just leave it as A. So let's just start here. Mu S, we're just going to call that S. And they tell us up here what that value is. Mu S static friction is 0.6. Mu K is 0.2. So this is 0.6. These are the values we're going to end up plugging into our into the calculator, the variable values we're going to set. M1, we'll just call that M, will be M1, and it is equal. So I'm not going to keep scrolling back up. I have this visible on a second screen, so I'm just going to reference it there. Oh, it tells us the diagram. M1 is 4 kilograms, 4.0 kg. This is meters. We're going to use N for M2. That's often what we do when we're trying to put these things into a simple calculator like a TI. Since it can only use one letter variables, if we have two masses, we'll call one M and one N oftentimes. M2, which is 3 kilograms. Okay. G is, of course, 9.8 meters per second squared. We'll use K for mu K for coefficient of kinetic friction, which it says is 0.2, and coefficients of friction are unitless. We have M1 already, we have M2. All right, we have all of the pieces we need. So now we need to calculate this A value, and then we need to plug it into this time. So what our equation is going to look like is A is actually going to be equal to, this is what we'll type into the calculator, SMG divided by N minus K parentheses M divided by N plus 1 G. And in fact, what we'll do there we go. And then we'll store that in A, right? So that's what we're going to type into the calculator. Then, so this is, actually, let me label these. These are, oops. These are calculator variables. These are our calculator expressions. We'll type that in. And then we'll also type in square root of 2D divided by A. And if we wanted to, we could store that in T. But this will be our final answer. Final answer. All right. So let's do it here. I have to adjust my screen share so you can see my later. Okay, so it looks like you can see my calculator. So the first thing we're going to do is we are going to make the calculator disappear, apparently. You know what, calculator? You got to cooperate with me a little bit. Sorry, y'all. Give me just a second to... There we go. Adjust the size of this so the whole thing will fit on the screen. There we go. Okay. So very first thing is we're just going to type the variables into the calculator. 5, store it in D, right? Our alpha gives us access to the variable letters that correspond to most of the keys on the face of this. And then we hit enter. And now 5 is stored in D. 0.6 will be stored in S. Nope. Be stored in S. 4. And notice I'm just typing 4 rather than 4.0 because the calculator understands it as the same thing. M3 is in okay, I'm going to take a screenshot of this to put into the Miro board. Okay. All right, and we'll keep going down. what do we need? We also need G, so 9.8, store that under G. The way my emulator works is it's as if it's a brand new calculator just out of the package every time I turn it on. I can save the state, but it's a pain in the butt. So I don't. On your physical calculator, any variables you store, unless the batteries go dead, those variables stayed in there. So if you save 9.8 as G, you don't have to re-input it every time. In fact, what you could do to check, if you just want to double check that your G is correct, you can just hit alpha G, right, and hit enter. And if it tells you that it's correct, then you're golden. All right. And then 0.22. Oops. Store that under K. Excellent. Okay. Now we will also grab that one. Okay, so all of our variables are now stored in the calculator. 1, 2, 3, 4, 5, 6. Okay. So now what we need to do is just type in that first equation, including we'll use the store arrow, and we'll store the value as A, whatever this calculates, we'll store it automatically as A so that we can just plug A into here, right? So we are doing, oh look, and actually here's kind of a cool thing you can do. There's an alpha lock button. So if you hit second and then alpha, now you don't have to keep hitting alpha before you hit every one. So I can just do S, oops. M, G, but now I do have to undo it because I need oh, here, and I'm going to move this over here so you all can see the equation we're supposed to be typing in. So now that I have the variables typed in, I can come over here and I'm just typing this in. And so I hit alpha so I can hit divided by alpha. We need to divide by n. So we'll do n minus K parentheses M divided by N plus 1, close parentheses, and finally times G. And now I could just hit enter and get the number, but in addition to that, now I'm going to hit store, and we get the little arrow, and I'm going to hit A. And now it's going to calculate it and also store that value in A, right? You can do both things at the same time, which is really nice and powerful. So then I'm going to hit enter. Okay, looks good. Take this. Paste it over here. All right, there's that value. And now I should just be able to do this square root and type that in. So where's our square root? It's right there. So second, that gives us a square root. We need a 2. We need a D. We need divided by, and we need an A, which is the A we just typed in. And then we'll get outside the square root. And now I could store this as T if I wanted to. If we were then if there was another part of this problem, we're going to have to do something with that time, I could store it as T, right? Isn't that useful? I am going to store it as t because as soon as I hit enter, boom, look what we get. And we can see, hopefully you can see all those now. Sorry about that. They're a little behind the screen. And there we go. Right? See how painless that is? It is a little tedious, granted, right? It's even a little bit more tedious for me because I have to double tap every button on that emulator I'm using for some reason. I'm not sure why that's happening. I think it has something to do with my touchscreen. But notice we didn't have to we just had to figure out what our variables were, what the shape of our equations looked like. I really, really do recommend taking this step, writing out your calculator variables, what you're going to store them in under your calculator. Make that plan ahead of time, and have it written down someplace so you can re-reference in case you forget. And then take another opportunity to rewrite the thing you're going to type in terms of those calculator variables that you stored, right? That way you don't have to do the translation in your head. You're like, oh, mu-s, is that, wait, was that s or was that m? What was that? Did I use a u? No, you just have it right over here. You have the equivalence between the equation variables and the calculator variables along with their values. And then you know exactly what you're going to type into the calculator. So you can plan all of this out. And then the calculator is just a tool that just crunches all of the numbers for you, which is its entire purpose, right? People get intimidated by using their calculators though because they often don't feel like they fully understand what the calculator is doing and or how to organize their thoughts and stuff like that because they're trying to calculate just SMG. Then they divide it by n, and so that's a number. Then they divide it by n, and that's another number. Then they're like, okay, but now I guess I have to calculate m divided by n plus 1, and that's a number, and multiply it by k, and that's a number, and multiply it by g, and that's a number. And now I have to go back and get this SMG divided by n number and subtract this other number, right? That's a lot of steps, but the calculator can do the whole thing for you all at once. Look what we get, though. Boom. The time is indeed 1.7 seconds. Boom. How about that? And some students, if you're in high school or you're still early in college or something, some students might still have this sense that's been instilled in them that a calculator is kind of cheating or something, and it really, really is not. Calculators are a tool, just like a computer, right? We almost never have you handwrite essays anymore. That used to be a thing, and in fact, actually, people were worried about students if they typed it on a computer that they might cheat somehow, right? But no, calculators are a tool. You just need to know how to use them. And notice all the calculator did was crunch numbers. We had to know how to solve this problem, right? We had to set up the equation correctly. We had to know what the values of the variables were. We had to put them in the right place, all of that stuff, right? So all the calculator does is crunch the numbers efficiently. And that's usually the least efficient part of doing a problem like this, is if you crunch the numbers sort of by hand or partially by hand by calculating parts of the equations at a time. That can also, if you don't keep enough decimal places, that can also lead to a lot of some rounding errors and stuff like that. So yeah, this is an efficient way to do it. There we go. Nifty. Okay, so there's that one. Let's look at the next one, shall we? The next one is long and has has 5 questions as part of it. I haven't looked at them yet. So some of them might be really short. They all might be really long. We'll just have to find out together. Probably just tell me that I'm live. Okay. We also want this timestamp. Where are we at in the video? We're at 1:06:30. And we will put a stream marker. Hey, look at me. This is really excellent. Okay. So now that we have that, let's actually read through this problem. Can bacteria coast? This continues our discussion from class. So, okay, something like this was discussed in class, but this problem is self-contained. Very good. Many bacteria swim by actively rotating flagella that act as little propellers. For small objects or low speeds, the drag force is this equation. So the drag force is negative b over v. V is the speed, and b combines several factors, probably the viscosity of the liquid, maybe even the size of the flagella, things like that, the speed of the flagella. I've included a negative sign to indicate that this force acts in the opposite direction as the velocity. Oh, sure. Drag force is a friction force, right? So like if you're moving through water or moving through air, the fact that like at normal walking speeds, we don't experience this very much, but you do experience it when it's really windy. You feel the wind pushing on you. That's effectively drag. Uh, Especially if you're moving. It really drag is when an object moves through what we otherwise consider probably still air, right? You have to push that air out of the way for you to move through it. Or if you're in water, you have to push the water out of the way, and water's heavier, so it creates more drag. But yeah, it's basically a form of friction. Okay. For a sphere, b is equal to 6 pi. Oh, what is that? Is that a new? Ba, 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 ba. It looks like an upside down mu. Oh, is that a zeta? It just looks weird here in the typographic. Um, no, it's not a zeta. It's not a lambda. Oh, here it is. I just kept missing it. It's an eta. Eta.
Eta.
All right. That is an eta. Learn our Greek letters, right? And we'll make a note. This is lowercase eta. Very good. Okay, sorry. I like to make sure I know these. I want to be able to say them as I'm reading them, right? I don't want to just call it the little n or the like weird n or something like that. Like it's an eta. So we have, okay, so that B value is 6 pi eta r. Eta is the fluid viscosity. Figured that was in there. R is the radius of the sphere. So yeah, that makes sense. We're going to pretend the bacteria is a sphere because the actual shape hardly changes the results, and using it would just make the equations longer. Yeah, this is oftentimes what we do in physics, right? You assume something's a cube or oftentimes a sphere because the actual difference doesn't make that big of a deal. But if you are in a real life, in an application, you're doing real engineering, you would start assuming it's a sphere, and then you would add in the extra complications and see how it changes things. And sometimes you realize it changes things so minorly that you're not even going to bother with the extra complication because the results are negligible. But sometimes they aren't. So we often start with an idealized scenario to start off with to get a handle on the situation, and then sort of add in complications as we go. But all right, so we have a spherical bacterium. Okay, suppose a bacterium of mass m has speed v naught and then stops rotating its flagella. How long and how far can it coast before it comes to a stop? We'll break this into pieces. You can ignore gravity; it is irrelevant, and you can ask yourself why later if you want. It's suspended in fluid. It's buoyant to some degree, and it's so tiny that gravity is not really going to be a factor. Note that the bacterium has a known initial speed v naught and in general an unknown speed v of t. We don't know what its speed is at any given moment necessarily, but we do know that it had an initial speed. How long? And it has speed v naught. Oh no. Yeah, that's its initial speed when it stops using its flagellum, actively propelling itself forward, right? And so it's just going to coast. That's what we mean by coast. Okay, so we have some stuff going on here. Let's see what the questions are, shall we? In terms of the symbols m, b, and v of t, write an equation for the acceleration a. This part is very short, it says. Okay, so again, remember, it is no longer, so this acceleration is a deceleration, right? So we start from Newton's second law. right? This is always true. And in fact, because we are expanding this side, I like to put it on the right. Okay. So, what is the force? The only force acting on it is the drag force, right? We can make a note here. Once it stops rotating its flagellum. What a weird word. Flagella. I guess it only has one. Its flagella. The only force is the drag force. Okay. The only force is the drag force. It's negative. But we're going to get the negative when we substitute. So I'm not going to put a negative here, right? This is negative because it's going against the direction of motion. But we're going to get that when we substitute and get negative BV. Right? Okay, cool. And there we go. We need MB and V in there. So we get MA, MA. So now we solve for A, divide by M, divide by M. So we get A is equal to negative BV over M. There we go. Cool. And then, yeah, that negative indicates it's a deceleration. It's going the opposite direction of the motion of the velocity. All right. Yep. That was very short. All right. Let's see what's next. One thing to pay attention to is so like this problem, it set up an initial question. And here, let me paste this, and then we'll go back and we'll talk about what that initial question was. It set up an initial question. How long and how far can it coast before it comes to a stop? That's ultimately the question we're interested in answering. Right? And the problem, these A, B, C's, and D's are walking us through the process of answering that question, right? And so when you're in a class like this, one thing to pay attention to is not just how do I do each of these individual things, but understand that they're actually teaching you a process by doing this. Because on a test, they might just ask you this question: how long and how far can it coast before it comes to a stop? And they may not break it down into parts A, B, C, D, and E, right? They want you to do each of those parts on your own. They want you to understand that that's the process you need to go through, right? And their logic is, well, there was a problem just like this that broke it down. That's the learning part. And then when we test you, we hope that you've internalized that process, right? So it's not, when you're studying for things like this, it's not just, can I do part A? Can I do part B? Can I do part C? It's understanding, oh, I need to know what each part is doing and how it leads me to answering that final question, right? So if we're asking ourselves how long and how far can it coast before it comes to a stop, yeah, we need to know its acceleration, right? Um, because its acceleration tells us how much its speed is decreasing, and based on how much its speed is decreasing, that tells us how far it will go, right? As its speed changes until it finally decreases all the way down to zero. Um, so yeah, um, so we found thus far we found an equation for the acceleration. It's still in terms of this b value, but that's okay. Now let's see what part B does. It says, now let's use the fact that A is the derivative of velocity. It's just the rate of change of velocity. We knew that. Substitute this for A, this was say in your equation from part A. If you're comfortable solving this differential equation to determine V of t, go ahead and do it. If not, do the following. Show that V of t equals, this is a solution of the equation you've written. This means that this is, okay. So they want us to find in a V of t, which is not just a velocity, 3 meters per second. It is a equation for the velocity. It's how the velocity is changing over time, which is basically what acceleration tells us anyway. We could do this problem probably with just kinematic equations, but they're trying to help you lean into a sort of more active sort of problem solving where you don't need to depend on equations you already know. You can actually figure things out from mathematical principles. Okay, so we know that A is dv over dt, which is equal to negative bv over m. So what we can do here, so we're gonna do separation of variables. And we're gonna do times dt times dt, and then we're also going to do divided by v. Actually, I'll do these in two separate steps. So this will be dv is equal to negative bvm dt. And now we need to divide by v to cancel out the v, divide by v. And so over here, we can write it as dv over v, but I'm actually going to write it as 1 over v dv is equal to negative b over m dt. And now we anti-differentiate or integrate to remove differential terms, which are dv comma dt. So we do this, blah, blah. Remember, b and m, those are constants. Those aren't variables. V is a variable. The dv tells us the variable. Over here, the variable is t. So this is just some fraction, some negative fraction. Okay. Coffee. So over here, the antiderivative of 1 over v, or 1 over, your variable, is just natural log of that variable. Natural log in a absolute value. Technically, that's not going to matter for us too much. And here, so this is just some fraction, right? So it's essentially, we could bring that out front. So it's basically just the integral of dt, which is just t. So the result of this is negative b over m times t. And then we have some constant of integration there. Yeah. Ba, ba, ba. So to find constant of integration, set t equals 0 and v equals v0, right? That's the initial velocity. Yeah, we'll go ahead and do that. So for just a second, so we'll get, so it's like a little aside here. Here, I'm going to change this to purple just to make it contrast a little bit. There we go. So we're going to do natural log of v naught equals negative b over m times 0 plus c. So this is natural log of v naught equals c. So this is v naught equals e to the c. Oh wait, we wanted to solve for c. Huh? Never mind. I solved for v naught. That's not what I need to do. I need to solve for c, and we have it. Boom, boom. Okay. So then we go boop, boop, and we do natural log of v is equal to negative b over m t plus natural log of v naught, the natural log of the initial velocity. Oh, and here I'll put that in purple actually, just to show us where it came from, plus natural log of v naught. There we go. Oh, I need to give my cat a pill. So I just noticed it was time for it. It's actually past time for it, but not by much. So I will, if you'll excuse me for just a moment, I'm going to go do that, and I will be right back, and we'll pick right back up here. All right, I am back. All right, I am back, which means volume is working. There's that. Sorry about the infinite um, recursion there. And we can dive back in. Okay. So this v that's in our natural log here, that's v of t. That's the function. I just haven't written it as v of t, just to keep the notation a little bit simpler right now. And our goal now, we want to solve for this. Well, the way you get rid of a natural log is you exponentiate. You raise everything. So now we're going to, oops, that's red. Solve for v. So we put everything up in the exponent of an e. That'll cancel out the natural log. And we can just call this v. We don't even have to actually worry about the absolute values now. Because it doesn't matter what you plug into an e, it's going to be positive. And so this becomes e raised to the negative bmt plus natural log of initial of v naught, initial v. But we can rewrite anytime you have addition inside of an exponential, you can rewrite that as multiplication of two separate ones. Oops, two separate exponentials, I mean. Oh my gosh. Here, I'm so sorry. Let me try to write that a little bit nicer, huh? Oh, and again, the notes are available. These notes that I'm writing in are available in a description below this video. There's also links on the website, thecalculustutor.com/live, where you can go. And that way you can scroll around the notes on your own, right? As you're like following along with my explanation. Because I need to write fairly large so people can see it, which means stuff goes off screen pretty quick. But yeah, so this is going to be equals. So we're going to get e to the negative b over m times t, and then all of that is times another e raised to the natural log of this absolute value of v. And then here, just like over here, e and the natural log cancel out. They also cancel out over here. So we're left with e to the negative b over mt times, and so this cancels out and just leaves us with the v naught, which means we can bring that around to the front. And so finally we get v of t, because it is a function of t, is equal to the initial velocity times e to the negative b over mt. There we go. And now we have done it. We solved that differential equation. Differential equations are fun. They're just so useful. And they're fairly straightforward a lot of times. Okay, so we now have a velocity equation. We know what the velocity is at any given time, right? Okay, cool. So then what else do they want us to do? So remember, we're trying to figure out how far and how long it can coast. So since we have a velocity equation, it starts at some v naught. It stops coasting when its velocity reaches 0. So we could set this equal to 0 and solve for t, potentially. Let's see if that's what they're going to have us do. That was part B. show that position x of t is therefore this. Oh, okay. Oh, so we're getting to okay, so if we want to figure out how far it goes, right? So uh we know final velocity is going to be 0. So we can set this one equal to 0, solve for t. Then if we know how long it's traveling and we have a distance equation, we can plug that t into our distance equation or position equation. And it will tell us how far it went during that amount of time. But we need to get this equation first, right? So how do we do that? Well, velocity v of t is just the derivative of position with respect to time. So this is just equal, so this derivative is just equal to the velocity equation we found earlier. And now we do separation of variables. We have another differential equation. A differential equation is just an equation that involves the derivative of the variable, of the term, the function that you're interested in. Oftentimes, it involves both the function and its own derivative, but basically any equation that has a derivative value in it is a differential equation. Okay, so we're gonna multiply by dt here, multiply by dt over there, and we get dx is equal to v naught e to the negative b over mt dt. And now we want to just like we did before, we will integrate, integrate to remove differential terms, which in our case are dx and dt, just like we did before, right? That's how you solve differential equations. Well, like ultimately, you're probably going to be taking antiderivatives or integrals to solve them. For certain classes and certain ones that have certain complexity, you don't do that. There's other techniques. But this is the classic way to do it. Separate your variables, get anything that has to do with t, including the dt on one side, everything that has to do with x, including the dx on the other side. You want your differential terms, dx and dt, to be in the numerators. And then you can just take an integral of both sides. Oh, I should get rid of that. There we go. That equal sign. So over here, this is just the derivative of x, or sorry, the integral of dx, which is just x, right? Dx is the derivative of x, so its antiderivative is just x. Boom, we get that. And then over here, v naught, that's a constant. That's just some number. It's its initial velocity. That doesn't affect anything. B and m, constants. So this is e to some constant times t. So so that v naught comes along for the ride. It's just a constant multiplier. The way the antiderivative of this works is exponentials are their own derivatives, but then we have to account for whatever the multiplier is. And the way we do that is we end up multiplying, when we're taking an integral, we end up multiplying by the reciprocal of that. So we're going to get negative m over b. And then it's just going to be, its derivative is just going to be, its antiderivative is just going to be itself plus this reciprocal constant term. There we go. And then, of course, we have our constant of integration. However, to find the constant of integration, just this is what I did in a different color previously, so let's call it, oops. Come on, you're on board. Let's call it purple. Set x equals 0, t equals 0. This is because initial position is 0. Okay. So up here we'll go 0 is equal to v naught negative m b e negative b m t oops, except this is a 0. Finally plus c. So negative bm times 0 is 0. Anything raised to the 0 is just 1. So this becomes, so we get 0 is equal to v naught negative m over b plus c, right? So we will add v naught m over b. That'll cancel out, plus v naught m over b to both sides, and we get that c, that the v naught m over b is equal to c. Okay. So now x of t is equal to v naught negative mb e to the negative b over mt plus v naught m over b. So what we're going to do is we're going to factor out, these both have a v m over b, so we're going to factor that out. So we get, bring the vo m over b, right? Then what that leaves behind is a negative from this one, e to the negative b over mt. And then if we factor all this out, it leaves behind a 1. So we can rearrange that. Oh, that's lowercase b. 1 minus is the way they wrote it. There we go. And we'll even call this an x of t. Actually, no, we'll just call it an x. And we'll say x equals x of t. There we go. Yep, we get exactly what they got. Boom. So now we have a velocity equation and we have a position equation for this bacterium based on just those essential values, the m and the b. and the initial velocity, whatever it was. So I imagine what they'll probably have us do is set the velocity equation equal to 0. They'll probably give us a value for v naught, and have us solve for t. And whatever that t is, we can, in part E, they'll probably have us plug that t value into the x, and we'll answer both of the questions, the how long and how far. Okay, actually, no. They're doing it slightly differently. So this is interesting. Okay. So it says, what is x of t? So they want us to take a limit. They want us to figure out what is the limit as t goes to infinity for x of t, which is the limit as t goes to infinity. And this does make sense as a way to approach this problem. Right. Eventually it's going to slow to a stop, but it's one of those things where, like, when you're coasting, like, you're slowing. Eventually you do stop, right? But there's a little while you're barely moving at all. But eventually, say it takes 5 seconds to come to a complete stop. It's not going to travel any further if you wait another 5 seconds. So if we go out to infinity, whatever that is should be its coasting distance, which is kind of an interesting way to do this. VO m over b 1 minus e to the negative b over m t. Okay, so we're taking that limit, right? These values don't care about the limit. The 1 doesn't care about the limit. The only thing that cares about this t going to infinity is this. Here's the thing, though. So this is a negative number. So t up here, this is actually, if t is going to infinity, this is e to the negative infinity, right? So we'll make a little note for ourselves, right? We'll say note limit as t goes to infinity for e to the negative t, that's equal to 0. And if you're not sure why, here's the graph of e to the negative t, right? This is e to the negative t, right? And notice as we go to positive infinity, this is going down. It has a horizontal asymptote at 0. So the further you go out, the closer this gets to 0, which means this whole thing right here goes to 0. And that's us using our limit. So what we get is the limit as t approaches infinity for this distance function, x of t, is equal to just this stuff right here, VO m over b. And now we have, which is kind of neat, we now have a formula for the coasting distance of a bacterium, right? Whatever speed it was going when it stopped actively propelling itself forward, you multiply that by its mass and divide it by that b value, which is sort of a combination of a bunch of different things, right? Excellent. So what can we say? We can say the coasting distance is given by VO times m over b. That's what we can say. Okay, that's not actually how I thought they were going to have us do it. They had us figure out the coasting distance first, which is kind of interesting. Okay, so God, what's part E going to be then? I do wonder. Let's see, let's see. Okay, now some rough numbers. Okay, for a bacterium, the speed, so they give us that initial coasting speed, gives us a mass. These are tiny numbers, right? It's a bacteria, remember. So its size is very tiny. It can't go, because it's tiny, going fast for it is still very slow. They give us a value for that. B, all these are SI units, so they'll give you X in meters if you've done things correctly. What's the coasting distance in meters? You should be amazed. Okay. So we never actually, it walked us through all of these. This is the last problem. We never actually answered the question, um, how long. We never actually got the time, but that's okay. We could figure out the time if we wanted to. But this question just focused on the how long, or sorry, how far. Um, okay, so we know coasting distance equals VO times M over B. So we're going to do some calculator variables right here. We're going to use V for VO, and that's going to equal 1 times 10 to the negative fifth, so we'll just call it 10 to the negative fifth. We'll use M for M. Right, they're both M's, but you can only use capital letters in the calculator, so I still like to be really explicit here. This is going to be 4 times 10 to the negative 15. I guess we can put units here, meters per second. This is kilograms. And we'll use a B for B, which is 2 times 10 to the negative 8 Newton seconds per meter. That's a weird unit. Okay, so those are calculator variables. Here are our calculator expressions. So I'm trying to model a good way for you to approach doing problems like this, right? So what are we going to type into the calculator? We're going to type in V M divided by B. Pretty simple, right? And now that we've done all of this, we don't even have to worry about all this stuff up above. Our task now is just the calculator, right? So we'll come over here and we'll turn it on. Turn on. Hey, turn on. There we go. I'm going to clear my screen. That doesn't actually clear the variables. They're still stored. That clear just clears the screen. So we're going to do 10 to the negative fifth, and we're going to store that in V right there. Boom. This is how the calculator displays 10 to the negative fifth. This is called engineering notation. So we got to do 4 times 10 to the negative, oops, 15. And we'll store that under M. There we go. Yep, see, there's that engineering notation again. And finally, we will do 2 times 10. You can actually use the engineering notation directly if you want to, but I think most people are more familiar with this scientific notation. Negative, what is it, 8? Nope. Store that under B. There we go. I'm going to enter. Cool. Print the screen here. Boom. And then, okay, so we have that all in there. So now we move this over here and we go down and we just type in alpha V alpha M divided by alpha B. Oops. Sorry about that. I don't know what I hit. I just hit a button on accident. I'm gonna hit enter. All right, and we'll capture that. So this is 2 times 10 to the negative 12 meters, which is picometers. What is pico? Prefix. Yeah. This is 2 times 10 to the negative 12 meters. So we can say the bacteria will coast a distance of 2 times 10 to the negative 12 meters, or 2 pico or picometers. I'm not actually, I think it's said both ways. Boom, there we go. It says the question itself said, you should be amazed. I don't know why we're amazed. I don't know if we're amazed because it's just very, very small. We expected it to be very small though, right? It's not going very fast. It's probably in some sort of fluid, so the viscosity is very high, which means it's resisting the motion. If it's not actively pushing against it, propelling itself forward, it's going to stop very quickly, which means it's not going to travel very far because it wasn't going very fast, right? And there we go. So I guess I just mostly want to point out that our process, pay attention to the processes that are really similar that I use. I'm trying to model good problem solving processes for you, processes you can use when you're doing your homework, when you're doing quizzes, tests, things like this. You know, these extra, what might seem like extra steps of spelling out your calculator variables, spelling out your calculator expressions, they Doing those sorts of things are the types of things that will help you feel confident about the work you're doing. So if you're somebody that that often struggles to feel confident during a test or on a quiz or anything like that, developing habits like this that you can rely on um, is one of the things that you can do to increase your confidence, your overall confidence as you're approaching problems and things like that. Yeah, that is it was just two more problems, but they were pretty long. Um, and that's all I got for you today. I will be well, I'll probably be back tomorrow night. Um, my sleep schedule has changed. I'm not up as late as I have been, so that late night stream is not actually working as well for me as it used to. Um, so um if I don't have anything to work on, I'm probably not going to do the stream. So we got this bonus stream, and we'll see if we get one tomorrow. It just depends on what sort of questions I get from my students or from other people. Um, all right. Well, I think I will call it here. Hope you all have a good afternoon, and I will see you tomorrow. See you Wednesday. See you Sunday. I'll be back though. There will be another stream when I have questions to answer. Bye.